This is a lesson on functions and their inverses in a precalculus course. I wanted to start with the definition of inverse function. What is the definition? It's a function for which the input of the original function becomes the output of the inverse function. Okay, so in our picture down here, we have the original x. If we have some sort of function happening on it, we don't know what it is, any sort of function, we get an output of y. And what an inverse function is saying what function, if I took that output y and put it into that function, I would get my original input back. All right, we denote this with the inverse function, and it's notated with f to the negative 1 of x. The inverse of f, or f inverse. Please note that f, the inverse of f, is not just taking 1 over f. We're going to call that the reciprocal. I know before this point in math, you may have called the inverse this the inverse, but this is the reciprocal. The inverse function has a very specific definition that has to do with this input and output stuff. It's not a simple 1 over situation. And what we're going to notice is that inverse functions undo one another. If I put x into one function and get that output and put it into the inverse function, so if I take the output of the one function and put it into the inverse function, it's inverse, I should get the output back. Okay. Inverse functions need to be 1-to-1. Remember, if I get two outputs here, I can't put two outputs as inputs into here and get a function. They both need to be functions, which means they need to pass this line test for both of them, which means the original function needs to pass the vertical line test too. All right, so it must pass the horizontal and vertical line tests. F must be 1-to-1. So that's the definition of an inverse function. We're going to look at some properties of the inverse function, and the first property we're going to look at is, of course, the algebra of it, which I was just talking about. If I take an input and get outputs and what's going on with that, what was the original function? So basically what we're going to do is look at the definition. It says the input of the original function becomes the output of the inverse function. And what that means is we're going to switch the x and y variables. I have this example for converting degrees Fahrenheit to degrees Celsius, and I'm going to put a pin in that for 1 second. What I wanted to do was do an inverse if something is a line. Let's just pick a line. 2/3 x plus 5. That's a line of slope 2/3 x. We're going to find the inverse of this line. And you don't play simple games like making stuff up like it's -3/2, minus 5 or something. It's not that easy. What we're going to do is we're going to switch the x and y variables in the equation and solve for y again. So this we could represent as a y, right? Y is all of this stuff. So if I do f -1 of x and say that is the x value, right? We're switching the x and y variables. So wherever I see y in the original equation, I'm going to put x, and wherever I see x in the original equation, I'm going to put y. And then I'm going to solve for y again. Okay, so there's the y. I'm going to solve for y again. So in order to isolate y by itself, I need to move the 5 over to the other side first. I'm going to subtract 5 on both sides first. Now to isolate y, I'm going to multiply each side by 3/2. And this side, 3/2 for the whole quantity, right? It's multiplied by that whole quantity. So when I solve for y, which is the inverse function of the original function, I'm going to see that it's 3/2 quantity x minus 5. So if this is the original function, this is its inverse. And so that's the algebraic determination of it. I actually used algebra to do it. And so this is what the book says: switch the x and y variables and then solve for y again. And this is a reliable method to be able to find the inverse of a function. However, I see students struggle when it comes to like formula and variables. If I let degrees Celsius be a function of degrees Fahrenheit, right? If I want to find Celsius and I know what Fahrenheit I have, I would be able to find Celsius with this equation. However, it may be that I'm given Celsius and I want to know what Fahrenheit is. And so I can't just switch Celsius and Fahrenheit because this is not a true equation. This is not the correct relationship. I'm not going to switch that and have it be true. That's not the way to do that problem. What you need to do is just solve for this. If I want Fahrenheit as a function of Celsius, I'm going to solve for my variable Fahrenheit in there and have Celsius and everything else on the other side. So I'm going to isolate Fahrenheit. In order to do that, I need to multiply both sides by 9/5. So I have a 9/5 here and a 9/5 here. So 9/5 Celsius equals Fahrenheit minus 32. So if I want to find degrees Fahrenheit, I'm going to take 9/5 of degrees Celsius and add 32. That's how I would find Fahrenheit if I'm given Celsius. I think, doing this method over here is the definition and it works. But then when you start moving to in context, don't switch the variables. I see students do that and it throws them on a way different path. You think you're doing something right, but it's not what needs to be done. Let's do another example I see students struggle with. Let f of x be this rational function. We have a rational function here. There's a ratio of one function over another. We have a line and a line. And it says, determine the inverse when I evaluate the inverse at -2. Well, I'm going to break this problem into parts. The first thing I'm going to do is find f -1 of x. And then once I find f -1 of x, I'm just going to plug -2 in that function. All right. That's how I'm going to do it. And I'm going to do it algebraically so I can prove to my teacher I can do it algebraically. So the inverse of x, all right, what I'm going to do is I'm going to switch the x and y in the equation. In the original function, I'm going to put a y here. So when I do that, I'm going to see that x equals y plus 5 over y plus 8. I'm switching x's and y's. Whatever was a y, I'm making an x, and whatever was an x, I'm making a y. And I need to isolate y in there. You can see we're going to have a little bit of algebra to do. Don't make up algebra where you just like divide those y's for some reason. We're going to have to do some funky algebra in here. The first thing I'm going to do is multiply each side by the expression y plus 8 and get this to be just linear without any denominators in here. There's no denominators, right? I multiplied each side by y plus 8. I'm going to distribute. I get xy plus 8 equals y plus 5. I'm going to do some rearranging. This may look familiar when you first started factoring. Remember I want to get y on one side and everything else on the other. So I'm going to gather the y's up on one side and then everything else on the other. So I'm going to go x, y minus y equals, 5 minus 8 is -3, right? I'm going to subtract 8 over here and I'll get a -3. So I'm going to factor out a y here. I get y x minus 1 equals -3. So when I do this and I get the inverse here, you can see that it is a nice little expression, y equals -3 over x minus 1. Or you might write it like this to denote it that it's the inverse, -3 over x minus 1. Now I'm going to put -2 into it. F -1 and -2 is -3 over -2 minus 1. This looks kind of uninteresting. Is 1. I mean, it is what it is, right? It is what it is. But that's how I would do that problem, is do the algebraic transformation of that function into its inverse. And then once I find that inverse function, just plug that value in there. I wanted to cover a situation where we had a context, using inverses in context. Find the formula for the inverse function, right? What is P in terms of C? So we're going to do that in a second. I'm just going to follow this through, and to be honest, I like to put a problem like this on an exam. I remember actually using this exact problem on several exams in the past. I'm not saying that's the problem I'll put on an exam in the future. But I like this problem. We have a function of the cost to remove a toxin from a lake, and it's modeled by this rational function. You can see that's a rational function. I have a line over a line, and that ratio makes it a rational function. Where C is the cost in thousands of dollars, and P is the amount of toxin in parts per billion. So we have to remember that we're in thousands of dollars in parts per billion. This model is valid only when the amount of toxin is less than 85 parts per billion. So we're just going to limit this function to a certain, I'm sure after that it's much more expensive. Find the cost in dollars to remove 35 parts per billion of the toxin from the lake. Round to the nearest whole dollar. So this doesn't seem hard. It wants the cost of 35. I can have 35 in parts per billion. That's what it says here. I can have it in parts per billion. So I get 75 times 35 divided by 85 minus 35. And when you solve that through, I think you get 52.5. And remember, it's not $52.5. We're in thousands of dollars. This is $52.5 thousand. So if I just round that to the nearest whole dollar, I need a whole dollar, not thousands of dollars. That's going to be $52,500. Okay, so that'll be the answer for the first one. Watch out for that. I suspect students get stuck there. Find the formula for the inverse function. Okay, so what we're going to do, and this is a problem where I see students try to flip things around. What I'm going to notice is that C equals 75P over 85 minus P. So what I'm going to do is get P on one side and C and everything else on the other. I'm going to solve for P. Solve for P. I'm going to keep that equation the same and solve for P. So I'm going to start over here in red. Like on the problem before, I'm going to take 85 minus P. I'm going to multiply both sides by that denominator. I am going to distribute 85C minus CP. I'm going to make that a big C. CP equals 75P. Remember, we're solving for P, so we're going to have to get the P terms together. This is a P term here, and this is a P term here, so I'm going to move this over to the other side. So I get 85C equals 75P plus CP. I'm going to factor a P out of both of those terms and put C out front. I don't know. I like putting the constants and variables out front. Okay, so when I solve this equation and I isolate P, I get P equals 85C divided by C plus 75. Or you could do 75 plus C down here. Either though, it's the same equation either way. Okay, so that's going to be the inverse function. Notice that I didn't switch the variables and solved. I just solved the equation for the other variable. Okay, so use part B, determine how much toxin is removed for this many thousands of dollars. So I'm going to say the cost is this number divided by 1,000. The C value that I'm going to put in there is 50. Remember, I got 52.5 over here, so I suspect that this is going to be less than 35 because I have this number is less than this, and that was 35, right? So I'm going to plug into this equation. right? That's the advantage of this. I did the algebra, and now I'm just going to plug that value in. 85 times 50 divided by 75 plus 50. And when I plug that through, don't use 50,000, use 50 for thousands of dollars, right? 34 parts per billion. So that's how you do that problem, and a couple of places that I see students struggle on that problem. The last thing I wanted to cover here as we move forward, actually a few things, but it's related to the graphs of inverses. You're not surprised to know if I do something on the equation, it changes the graph. And when I look at graphs of inverses, very specifically, the input of the original function becomes the output of the other function. And what this does is it flips the graph over the line y equals x. So we're doing a mirror reflection over that. Do you see it? And it's not a reflection here and a reflection here. That's not an inverse. You think it would be that easy, is to do a reflection here and a reflection here. It's not too simple in reflections. It is specifically a mirror image over that line y equals x. So you have to be able to envision that line y equals x and then flip that function over it. And that's going to be the inverse over this diagonal line. And so I mentioned before is if you're given 2 points, and this is more, I think, specifically useful when you're looking at a graph, is if I'm giving a point on one graph, if I flip those, if the output and input flip, which we've been doing on previous problems, that's going to be the inverse. So like on this problem here, I can see that I have the point 1, 2. So on the inverse, definitely 2, 1 needs to exist. Does 2, 1 exist? 2, 1. And it's flipped over this diagonal line. Okay. Same thing for this function over here. It looks like I have half a parabola. There's half of a parabola here. If I flip it, let's see what it is. I guess this point is on both of them. That's not very useful. This point, 2, 4. So I have 4, 2. 2, 4 becomes 4, 2. And for me, when I'm looking at graphs, that's an easy way to do an inverse, is just to identify a point on the original and then flip it, and that has to be on the inverse. I have an example dealing with that, and I think students have trouble with this because they're not too aware of that's the trick. That's the trick of it, all right? We have a line, and I'm just going to graph this line. We have this point. The y-intercept we know is 0, 6. If I plug in 0, I get 6 out. That's our y-intercept. And then I'm going to pick another point. I could go up to and then over 3, or right? Rise over run up to over 3. That would give me this point here. I could do in the other direction as well, down to left 3. Down to left 3 gives me this point here. So when I do, so that's when I connect those, and you just need to pick 2 in order to graph it on the computer. If I want to find the inverse, what I'm going to do is just take those points, and if I have 0, 6, that means I'm going to have 6, 0 on my on the inverse. If I have 3, 8 on the function, then the inverse has to have 8, 3. So I'm going to find those 2 points. There's 6, 0. Then I have 8, 3. There's 8, 3. And so that is the other function, the inverse function, right? And when I look at this dotted line through here, and doing the best I can, I approximated it, right? Those two are a mirror image over that line. I think it would look a lot better if it went like this, right? It looks like that. And you can see those are mirror images over that line. Okay, so that's pretty easy if you're doing a graph of a function. Just find points and flip the 2 coordinates. So related to this in graphs of inverses is domain and range of functions and their inverses. And I had mentioned this before, that these functions must be one-to-one. We need one-to-one functions. My example here, you can see, is not a one-to-one function. Not at all a one-to-one function. If I was to choose part of the graphs to focus on, sometimes you might see that in a problem. They might say, do this graph, but do it only when it's decreasing or when it's increasing. So when I look at the original function, this parabola, if I divide it in half, on this interval of it, up to this point, it is 1 to 1. 1, 1, 1, 1, 1, right? There's one output for one input and one input for one output. The same's true for the right half of this, if I only go here. So you can see if it's decreasing, I can have a 1 to 1. If I limit it to that domain, decreasing, or limit it to the domain increasing, then I will have 1 to 1 functions. So we're going to have restricted domains and ranges. So we're going to restrict the domain. This is true maybe for a radical function. A radical function might look like this, and it has a restricted domain, right? So because it has a restricted domain, then the inverse, remember we're flipping outputs and inputs, then the range of the inverse is going to be limited. The domain of f of x is the range of its inverse, right? Because we're flipping those two, the input and the output flip. The domain of the original function is the range of its inverse. The opposite is true. The range of the inverse function is the domain of the inverse. And so that's what this picture is representing. If A is in the domain of f, then it's also in the range of the inverse. If B is in the range of the original function, then it will be in the domain of the inverse, right? We just flip the input and output. If a point is not in a function, then flipping it, right, that point where you flip the input and output will not be in the inverse. So that's when we're going to talk about limited domains and ranges. So let's look at a typical problem in this material. It says find a domain on which the function is 1 to 1 and non-decreasing. Okay, so again, we're going back to this definition of 1 to 1, and it's very specifically telling us when it's non-decreasing. Write the domain in interval notation for this function, then find the inverse restricted to that domain. Okay, so when I look at this is a parabola. We know that it's going to have a vertex at -7, 0, right? The vertex is at -7, 0. And when I draw it, I'm going to have something that looks like this. Yes, -7, 0. And it says find a domain on which the function is 1 to 1 and non-decreasing. Well, that function here is decreasing to this point. And remember, when we're doing increasing and decreasing, we read it from left to right. We read the graph from left to right. So from left to right, the function decreases and then it increases. So at its vertex is when it starts increasing. So we're going to have something like that. This is the part of graph that's decreasing. I'm going to leave it out, but it says when it's non-decreasing, so that means I can include this point is -7, 0 in my domain. So when I write this domain, write the domain in interval notation. I'm going to include this -7, and it's going to go infinitely in the x direction, right? In the x direction, it's going to keep going infinitely. So this is the domain for the original function. All right. I'm going to note that the range for the original function, let's write the range for the original function. The range for the original function looks like it can equal 0 or greater, right? It can starts here at value 0, and then it keeps going up and up and up and up. So that's the range. So when I look at f -1 of x, and I'm just going to do the domain and the range, I'm not going to do the equation. I'm just going to use what I know about the domain and range of the original function and use that to write the domain and range for its inverse, right? So what we know is that input and output switch. So whatever the domain was for the original function, that's the input, it becomes the output. So the range for the inverse function is going to look like this. I'm just going to switch them. The input and the output switch. So that means whatever was domain and range for the original function, it has to be range and domain for the inverse function. So let's write this. The domain for this one is going to look like this. I think that answers a little bit more than what the problem asks. It says find the inverse of f restricted to that domain. All right, so we do have to do some algebra. Let's find the inverse algebraically. What I'm going to do is note the original function equals y x plus 7 squared. I'm going to switch x and y in order to do this. So x equals y plus 7 squared. I'm going to have to square root both sides. And so the inverse function is going to be the square root of x minus 7. That equals the inverse function, and I found it algebraically. Let me show you the graphs. I think when you look at the graphs, this should make a little bit more sense. And I've said that repeatedly. If you're looking at domain and range, just graph it. You should be able to find domain and range just by looking at the graph. Of course, you know that I did this before. When we restrict the domain, remember I restricted the domain on the original function, and it looks like what it said that we wanted it to look like. It's a parabola starting at -7, and it's going upward. I dotted the part that we left out. That's the decreasing portion of the function. It decreases all the way up until this point, -7, and then it starts increasing. So when we look at this function, we want only what we call the right half of the parabola. That's the right half of the parabola. The inverse, you're going to notice the inverse. 0.49 is on that graph. I don't know why this came to the front. There we go. 0.49 is on the original graph, which means 49.0 is on its inverse. Okay, so that's good. And what we're going to notice is that we want the range, or sorry, the domain. We're going to notice that the domain starts at 0 and goes to infinity. We expected that. That's the domain. And then, I don't know why it happens. This print comes up front, and I don't know why. And then we want the range. We're going to notice the range. The restricted domain before was -7 to infinity. Now we have the range being -7 to infinity. Right? It starts on there, and that keeps our two functions 1 to 1. Both of those functions are 1 to 1.